So we need to talk about what is a limit. So we've been talking around limits today, but we haven't actually gotten to what is a limit. So we need to talk about what the limit is. What's the limit of a function? We've been talking around it, but we haven't actually gotten to it. So we're going to talk about the intuitive definition of a limit. We're not going to actually do the formal definition until section 2.5. Remember, it took from 1692 until the 1920s. That's a long time, right? That's about 250 years. It took 250 years almost before they could formalize the definition of it. It took a long, long time, all right, before they were able to do that. So they knew what it was intuitively, but it took Augustin Cauchy in order to actually formalize it. And we'll do that in 2.5. But here's the idea. We know we are not allowed to divide by 0 because it's one of our 10 assumptions that all of math is based on. Thou shalt not divide by 0. But what happens in the graph when x is 2? And I look at this graph right here, or I look at this graph here, or I look at this graph here. What happens in the graph when x gets close to 2? Does the y value get close to some number, or does it go to infinity, or does it go to negative infinity? So the idea of the limit is as x gets close to one thing, y gets close to something else, all right? So when we write it down, we're going to use notation that looks like this. We write the word lim, L-I-M, which is short for limit. And below it and in smaller letters, we write x approaches some number. And then here we usually have the function, which of course this represents the y value. And we want it to equal something. All right. So this says, what is the limiting value? As x gets close to 2, notice this is an arrow. This is not an equals. The arrow means it gets close to 2, but it never equals 2. And it can't equal 2 because if it equaled 2, I'd have division by 0. But it can get closer and closer and closer, never get there. What happens to the function's y value? That's what this notation is asking. As x gets super close to 2, does the y value, the function f of x, have a limiting value? That's the question. Does it approach a finite number or not? Well, here are the graph of those functions. So let's look at the one that's on the far left. So when you're looking at the one on the far left, this is the graph of x squared minus 4 over x minus 2. This is f of x. So I would say, and by the way, that scrawl that you see there is my lim. That's L-I-M. That's how I write it. So when you see that, that stands for L-I-M. X as approaches 2 of f of x. Does it have a limiting value? This is the idea of what are you aimed at, not what you hit. That's what a limit is. The limit is what it looks like it's going to hit, not whether or not it even hits anything, not whether or not it hits something totally different. What does it look like the y value is going to be? So if I trace along the curve from the left side, it looks like the y value is going to be 4. Does everybody see that? There's a hole in the graph at 2, 4. There's a hole. All right, but it looks like it's going to hit the hole from the left. If I put my finger on the graph and I trace it from the right, it looks like it's going to hit the hole. We call that a limiting value. The limit of the function as x gets close to 2 is 4. It looks like it's going to hit 4. Therefore, the limit is 4. It doesn't actually hit 4. In fact, it's not defined there at all. I don't care. All I care about is what does it look like it's going to be? What is the predicted value? That's the limit. All right. Let's look at the middle one. The middle one is the graph of g of x equals the absolute value of x minus 2 over x minus 2. So once again, thou shalt not divide by 0. We cannot have x equal 2. If x equals 2, it's undefined. So the question is, I've got 2 holes here. I've got a hole at 2, 1, and I've got a hole at 2, negative 1. So the question here is, what is the limit as x approaches 2 of g of x? Now I have a problem, because when I approach this from the left and x is getting close to 2, it looks from the left like it hits negative 1. Does everybody see that? From the right, if I put my finger on the graph and I pull it along the graph until it gets close to 2, it looks like it's going to hit 1. Those don't agree, right? From one side, it looks like it hits negative 1, and from the other side, it looks like it hits 1. If they don't agree, if they're different values, do you have one single finite real number? No, you've got 2 of them. Then we say it does not exist. All right, D and E does not exist. Okay. All right, what about the last graph? The last graph that we have over here is h of x equal to 1 over x minus 2 quantity squared. Once again, we cannot have 2 as the actual value of the x coordinate, because that would cause division by 0. Thou shalt not divide by 0. Full stop. Never, ever, ever. Right? But when we're looking at it and we put our finger on the left side of the graph and we trace it as it gets closer and closer to 2, where's my finger going? Where it's not going to a finite real number. Where's it going?
Infinite.
Infinity. Positive infinity, in fact. What about if I put my finger on the right side and I trace that graph? It goes up, 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 up to positive infinity. Now, is positive infinity a finite real number? First off, is infinity a number?
No.
No. So who told me no? Michael? Good. Yeah, you're right. Michael's correct. It is not a number, it's a direction. It's like saying go west. If you tell somebody directions to somewhere and you just say go west, that's not very specific. How far west, right? You need a number. West is a direction. Infinity is a direction. It's not a number. So technically, a limit of infinity does not exist, but we will write positive infinity to indicate that's where both sides agree to go. But technically, that means it does not exist. But we write positive infinity because it tells us something about the graph as the graph gets close to 2. As the graph gets close to 2 from both sides, it goes to positive infinity. So we write that knowing that that value is not a finite real number, and that means it doesn't exist. Okay. Let's now move on to the next part. All right, which is this one right here. This is one that your book skips at this point, which is bad. It should have it. The only way to have a displaced point is to have what's called a piecewise defined function. You guys remember these? This, oh, my bad. There it is. Okay, piecewise defined function. This could be the graph of something like, what's that look like? Almost looks like tangent. Tangent of x plus 1, and then, is that a C? I can't even read it. All right, this is the only way to have a displaced point. So when you're looking at the displaced point, what you've got is you've got a function for all the values except at one location. And at that one location, it's defined to be somewhere else, all right? Not where it looks like you're going to hit, but somewhere else. It's called a displaced point because the point's out of position, basically. So when you're looking at the graph, and Michael, I'm not sure this will show up too well for you, so I'm going to darken it. Right there, you've got a dark spot above the graph. Does everybody see it? That's the displaced point. It's out of position. It's at 3, not at tangent of x plus 1, which is where it should be. All right. So again, when we're looking at this kind of graph, when we're talking about the limiting value, if we trace along the blue curve from the left, it looks like it hits the hole. So we have a hole here at CL. And as we trace along from the right, it also looks like it hits the hole. It actually doesn't. It actually hits up here at 3. But we don't care because that's not what it looks like it's going to hit. That's not the predicted value. So the limit of capital F of x as x gets close to C is L. Even though the real value is 3, the limit is L because it looks like it's going to hit the hole. And so the y value at the hole is the limiting value, all right? So the idea of a limit is we're not actually going to ever get to C. We never actually get to C. We just trace along the curve from both directions. What does it look like it's going to hit? Whatever it looks like it's going to hit, that's the limiting value. So we've seen some examples of different things, and let me label these for you now so that you know what they're called. These are all breaks in what we call continuity. So I want to label them for you because we're going to be studying continuity from now on. Continuity is one of the most important conditions for the major theorems of calculus. Continuity means you can draw it without picking up your pen. That's the hand waving definition, which I can't do here because there's a hole. All right. So this first graph here has a hole in the graph. This second graph in the middle, do you see how it jumps up from one location to another without anything connecting the two pieces? We call this a jump. And this one here is what we call an infinite discontinuity or a vertical asymptote. In other words, we have a vertical asymptote, which is disrupting the graph, which is why I can't draw it without picking up my pencil. The fourth type of discontinuity, the fourth kind of break in the graph that you can have is the displaced point. All right. So the displaced point is the fourth type of discontinuity, change in continuity. All right. All right. We've done all of that, Notation, I've talked about notation, limits from the left and limits from the right. So I've not talked about one-sided limits. So now we're going to talk about one-sided limits. All right. So when we're looking at one-sided limits, they're exactly what they sound like. It says, come from one side only and talk about the limit from that one side. So when you're talking about it, we're talking about either getting close to some X value from the left or close to some X value from the right. This is the limit from the left, and that's kind of small, so I'm going to write it larger. As X gets close to A from the left of f of X equals L. This is a negative written in the power position. And it means from the left. From the left. Or you could say from below. All right. So let's go back to one of these graphs. I should have put a picture there, but I didn't. Okay, let's look at the jump. The jump is one that definitely has one-sided limits, but doesn't have the two-sided limit. All right. If I'm looking at the center graph right here, and I only come from values of X that are below 2, less than 2, I'm coming from the left. What Y value does it look like it's going to hit as I approach 2? So this is the limit. As X approaches 2 from below of G of X, what value does it look like it's going to hit? -1. All right. What about from the right? This would be the limit as X gets close to 2 from above of G of X, which is equal to +1. The reason the two-sided limit does not exist is because the one-sided limits don't agree. When the one-sided limits don't agree, then the two-sided limit does not exist. The limit from the left is -1. The limit from the right is +1. Those don't agree. Therefore, the two-sided limit does not exist. How do you know you have a two-sided limit? A two-sided limit does not have a sign in the power position. It just has X approaches 2. It doesn't have a plus or a minus up here in the power position. So we can talk about a limit from the left and a limit from the right on jumps, all right? And they do have limits from the left and from the right. So the limit from the right, ooh, that doesn't even look right. Is that right? There we go. It's a plus. All right. Now, if it goes to infinity, then we'll write infinity, but technically that means the limit does not exist. All right. These are infinite limits. Now, hang on just a second. My dog is going berserk. I'll be right back. So in the meantime, ponder infinite limits from one side or from the other, and I'll be right back. Okay, sorry about that. All right, where were we? Infinite limits. Okay. An infinite limit from the right or from the left is when we're talking about the graph going up towards infinity from the left or from the right. So if we look at like this graph right here, where we're looking at the graph from the left and the graph from the right, this is at 2, which is where we have our vertical asymptote. So I would say the limit, and let's call this, I think it was h of x, as x approaches 2 from the left is positive infinity. as I approach from the left side, from below, from x values to the left of 2, it looks like the y values go to infinity forever and ever. And then if I do the same thing from the right, again, put your finger on the graph on values above 2, and then trace the graph, and you'll see that your finger is going off towards infinity again. So the limit as x approaches 2 from the right of h of x is also positive infinity. And note that these two agree. This is a limit from the left and a limit from the right. And because they agree, I can drop the from the left and from the right notation and just say the limit at 2 of h of x is positive infinity. But technically, this means the limit does not exist because a limit is supposed to be one finite real value. All right, one finite real value. And it's not one finite real value, it's going to infinity. Okay. And then we talked about that. And now we want to talk about some problem solving strategies. We are going to get better techniques tomorrow on evaluating these. We're going to have some better techniques, better ways of doing this. But for today, we're going to be stuck with tables and graphing. That's basically our two strategies today, is the table and graphing. And they're not great strategies. There are algebraic strategies, and these are better strategies, and we'll learn these starting tomorrow. All right, when we get into 2.3 and maybe 2.4. So if we can get ahead a little bit, that will help us when we get to 2.5. The more time you have on 2.5, just the better. So we may get a little ahead this week. I don't know. I doubt it, but we'll see. So to evaluate f of x, we can start by completing a table of function values. So when you're looking at these right here, you've got a table of function values. And when you're looking at these, you look at the values in the f of x columns and you decide whether or not they seem to be approaching a single value as you're coming down the column. All right, are they approaching one finite real number or not? And then you can also use a graphing calculator or Desmos in order to graph it and plot the function. And then you can look at the graph and you can use either the traced feature on a graphing calculator or your finger on Desmos and come from the left and the right to see whether it points to one particular value. So let's look at this graph right here. 1 over x minus 1 over x minus 1. So I'm going to have to write that down. Is it f of x? It doesn't say. And x is getting close to 1. All right. So we're looking at this graph right here, and we want to know what value are we going to get. So we're getting close to 1 from below and from above. So A is 1. So 1 minus 0.1 would be 0.9, 0.99, 0.999, 0.9999. Does everybody see those are getting closer and closer to 1, but from below 1? All right, 0.9, 0.99, 0.999, 0.9999. These are getting closer and closer to 1, but from below. And then up here, these are going to get close to 1, but from above. So this is going to be 1.1 first. 1.1, then 1.01, 1.001, 1.0001. Those are also getting close to 1, but from above. So now what we want to do is we want to take a table of values and we want to figure out what this is. This is a great time to use your graphing calculator. So if you have your graphing calculator available, go ahead and open it up. And I'm going to switch the view so that I can show you on the graphing calculator. So the first thing you want to do is turn it on, and then you want to check the mode. It should be in function mode, and I think mine right now is in polar. All right, so it should be on FUNC. All right, so I'm going to come down to the fourth line, highlight function, and turn function dark. Right, so that it's not on POL, but it's on function. And then when I hit the Y equals button up here, where's my Y equals? There it is. It should give me Y equals or Y1 equals, Y2 equals, Y3 equals. Oh, and it's giving me plots. I want my plots off. Fine. Okay. There we go. So now I've got Y1, Y2, Y3, Y4. Let's enter our function into Y1. I need parentheses around the numerator. It knows to divide before it subtracts. So I'm going to do parentheses, 1 divided by, hit the X variable button, -1, minus not negative. And then I'm going to delete the rest of what was in there. Delete, delete, delete. Okay. 1 divided by X, use the -1, close parentheses, and then do divided by, open parentheses, X -1, close parentheses. So it should look something like that. All right, so enter that in. Make sure you use the subtraction and not the negative. And then we want to click on table, which is over here above graph. All right, so it's above graph, but we may want to go into table set. So we're going to go into table set, which is above window. And we're going to tell it that we want to start at 1, and we're going to go by, I don't know, 0.1. All right, so we're going to start at 1, and delta table is going to be 0.1. And then when we hit enter, I leave the independent and dependent on auto, and then I hit table, which is on the far button on the second. And now it gives me the table of values. And then I can go in, I can change the table set, but this will give me 2 values. It gives me 1.1, which is -9.091. And it gives me 0.9 if I scroll up of -1.111. Now I go back into table set and I change my delta table to 0.01 and go back into table. All right. And it tells me that at point, and I'm going to have to scroll to find it, 0.99, I've got -1.01. And at 1.01, I've got -0.9901. So go ahead and repeat the process. Table set 0.001. And now I want 0.999, which is -1.001. Oops, my one's moved. It keeps moving on me. And then my 1.001 is -0.999. And then do it one more time for 0.0001. And back into the table, 0.9999. You got to scroll a bit to find that one. Looks like it's close to -1. And at 1.0001, it's kind of given up and it's giving me -0.9999. Anybody want to take a guess at what you think the value is going to be there at 1? These values look like they're getting close to -1. And these values also look like they're getting close to -1. And so from both the left and the right, it looks like the values are getting close to -1. So we say the limiting value is -1. All right. And we can graph it. Turn all this off. There it is. And we want to know what it's getting close to at 1. Now, is it defined at 1? Notice Desmos has a value there. And when you click on it, it actually pops up. Oops, I moved it. I gotta keep my hand still. And says at 1, it's undefined. But it looks like it's graphing over the top, but it actually has a hole there. And if you click right on the 1, it will say undefined. All right, but it looks like the value is -1 from the left and from the right. And that's the limiting value using a table. What we're trying to do right now is we're trying to make the connection between the graphs and the limit so that you get a real sense for what the limit is. So last time we were looking at a graph right here where we can see that at 1 it is undefined. It has a hole in the graph at that point. And so we talk about the limit as we approach that point when we trace along the curve from both directions, and we can still get to the curve. So when we're looking at the curve, and if I move, I'll get off the 0. There it is. All right. So as you're approaching from the left side, it looks like it's going to hit the value -1. And as you're approaching from the right side, it looks like it's going to hit the value -1. In fact, it doesn't hit anything because it's undefined there. All right. But that's the idea, the intuitive idea of the limit. Now, when we hand draw the curve over here, we probably should make sure that we note that that is in fact a hole. So when we hand draw the curve, we would probably do something like this and then make a great big hole there to indicate that that's a hole. All right, so that's a much better way of indicating that there is a problem at that particular point. All right, when you draw the curve. Okay, the next one we want to take a look at is doing the same thing. It's the intuitive definition of the limit using a table of values. So go ahead and take a minute and let's complete the table of values. So we want to figure out the functional values and what we think the value is going to be. We're going to use the graphing calculator in a different way today than what we did yesterday. Yesterday we used the table. Today we're going to use the actual graph. So go to your graphing calculator, turn the calculator on. Let me change the focus. All right, so now when you turn the calculator on, you want to go to y equals, which of course is going to be up here on the top, that button right there. So you're going to click on to y equals. If you have one that's in there, make sure you highlight the equal sign and make it not highlighted so that it won't show up. And so we're going to put this into y2, which is the second one, and I've made the first one no longer highlighted so it won't show up. Okay. So we're going to put in z minus 1 over z squared times z plus 3 all in the denominator. So what we need to do is we're going to use x as our variable, and we're going to put it in parentheses. So open parentheses, hit the variable button, which says xt, theta, and n, depending on which mode you're in, and we're in function mode. So the variable -1, close parentheses, divided by, Now open up a parentheses for the denominator, hit the variable squared, open more parentheses, the variable plus 3, close that parentheses, then close the denominator parentheses. So the denominator should look something like this, all right? And once you have it all in there, we're going to hit Zoom Fit. Now, Zoom Fit allows it to evaluate a good interval, or actually maybe we should go to Zoom Square. Let's try Zoom Square. Where are we looking anyway? What value are we interested in knowing what it is as it approaches it? If you look at the table, what value is it approaching as the table values get closer and closer? Okay, yeah, Brittany's right. It looks like it's getting closer and closer to 0. So as long as we have 0 on the screen, we should be in pretty good shape. But if we want to know what it looks like when we get really close to 0, we could set a screen window of maybe, oh, I don't know, -5 to 5. So we can go into the window and on the X-Men, put in -5, make sure to use the negative and not the subtraction, and then 5. So it'll look something like that on the window button, which is up here at the top, all right? And then we're gonna hit the zoom button and fit, and it's gonna fit the window to those particular values. So hit zoom, and then scroll down to zoom fit, which is 0, or you can do the other. All right. So this is the picture that I got coming off of my graph, all right? It's really not all that clear. It's probably a lot better in Desmos, but this is one good use of the graphing calculator where you can actually control it a little bit. So now what we want to do is calculate these values. So we're going to use the second button, which is here, the second button, and we want the trace button, which is over here, all right? Second trace gives you calculate, and we want to calculate a value. So second trace, and the first option on that screen is value. So we want to hit a value. And the value that we want, you can either put the number 1 in or just hit enter. And it says X equal now down at the bottom of the screen. And we want to put in -0.1. Make sure you use the negative, not the subtraction. It sometimes causes a glitch in the programming with the calculator when you use the minus instead of the negative. And then this gives us the Y value at the bottom. So go ahead and fill that into the table, and then go ahead and fill in all of them using second trace. You can repeat that over and over and over again. Right? Okay, so let's take a moment and go ahead and fill in our table with all these different values. This is another way of using the graphing calculator. So I got -37.93103, all right? Second trace gives me calculate a value, -0.01. Whoa, okay, -3377.926. All right. Okay, what's happening here? Second trace value, -0.001. All right, now I've got -33377.9. Does anybody want to make a guess at what's happening here as we get closer and closer to 0? Any guesses? Bless you, Aubrey. Okay, let's see. My guess is that it's approaching what value? Or is it approaching a value, or is it approaching a direction?
Approaching direction.
It's approaching a direction. And what direction is it approaching?
The left. Or is that down?
That's down, because this is the Y value. So as X approaches 0,
the y value is going to negative infinity. That's an 8. And just a couple more. It doesn't look like it's even doing it symmetrically, which is interesting. But it is definitely approaching negative infinity from both sides. So what would we write that the limit is? How would we write the limit?
It's negative infinity.
Yep, we would write negative infinity for the function. But that means technically it does not exist, right? Remember that whenever you have the function and it approaches infinity or negative infinity, that technically that means it does not exist, all right? Okay. And then the last thing, of course, is to produce a graph of this particular function, which this function is kind of hard to graph, but it looks like it's going to have a vertical asymptote at -3. Uh-oh, I froze my screen. I knew better than to do that. It'll come back. We'll just give it a second. Why do we know that there's an asymptote at -3? What is it about this function that lets us know there's an asymptote at -3?
C,
got-
C plus 3.
It's got z plus 3 in the denominator. And because it has z plus 3 in the denominator, z cannot be 3, -3. If z is -3, then we're dividing by 0. So we also have a asymptote at 0 because of the z squared. So we have asymptotes right here on the y-axis and at -3. And the graph approaches here and then comes down and lays very close to the axis, approaches 0. And on this side, it approaches like this, and then it hugs the line very closely, gets close to the x-axis again, or z-axis as we go to the right. And in the middle, it kind of looks like an upside down U. Kind of does something like that. All right. And that's what our graph does. And as it approaches 0 from both directions, it goes to negative infinity. So that's what we write. Okay. All right. Now we're going to spend more time graphing functions like this one tomorrow when we look at 4.6 part 1. We'll be looking more at graphing with vertical asymptotes and horizontal asymptotes. So we'll be looking specifically at how we know they're there. So this is something you should have looked at in college algebra, but if you didn't, we'll be taking another look at it with calculus tomorrow. Okay. Let's talk about problem-solving strategies. When we're looking at the table, that's one way of doing it, but it's faster to simply look at the graph near the value of A. So this is the method that we're talking about when we talked about the intuitive definition at the beginning of this section. So if the graph approaches one unique y value from both the left and the right as it approaches A, then that is the limit value. So we want to take a look at all these different ones that we have right here and see if we can find what their limiting values are. So the first one we have is the limit as x approaches -11. So we're going to come over here to -11. And as I approach -11, well, what is the graph doing as it gets close to -11? What does it look like the graph is doing? Is the graph staying still or where is the graph going? Is that -11? Yep, I think so. And we'll probably have to estimate this one because it's probably not going to be exact. We won't be able to get an exact value, but as I get close to -11, so -11 is here, and it looks like it hits the graph right about here. So from both sides of the graph, if I were to trace it from the left, it would mean I would be coming down, and tracing from the right, it means I'm coming up. It looks like it hits the value of 4. It looks like the value is 4, and in fact, it probably is 4. So the limit there would just be 4, right? What about the limit as we approach -2 from the right? So let's take a look at that one. So locate -2, but from the right means from the right side, so from above it. So we need to come from the right and go towards the left. So find the graph on the right side of -2 and trace along it. And as it gets closer and closer to -2 from the right, where's the graph going? What does it look like the graph is doing there? It looks to me like the graph is going to positive infinity. All right, which means, of course, technically that it does not exist. All right, now how do I know it doesn't actually have a value there? Well, because it does have a value there and it's solid below, it's a ball. So it can't be, it's going up in the positive direction forever. That's got to be like a vertical asymptote, but only in the upward direction. Now we've got the limit as x approaches 6. So locate 6 on the x-axis and then find the graph. Now this says 6 from the right because it's got a plus sign. So go to the right side of 6, locate the graph, trace along the graph until you reach 6. It looks to me like that hits a 5. So the value as we get close to 6 from above is going to look like it hits 5. Right? Let's do the one right next to it, which is what is the limit of the function as x just approaches 6? And then this one over here, the limit of the function as x approaches 6 from the left. So we're going to do from the left first, and then we'll do the two-sided limit. So we're going to do this one first. As x approaches 6 from the left, find 6 on the x-axis, go to the left side, locate the graph, trace along the graph until you get close to 6. What does it look like it's going to hit? It doesn't matter if it actually hits there or not. It's what does it look like it's going to hit? It looks like it hits 2. So we've got 2. Now we have a problem because the limit from the right at 6 looks like it hits 5. And the limit from the left at 6 looks like we hit 2. In other words, as you come from different directions, your fingers end up in different places. And because they end up in different places, that means that the limit at 6, the two-sided limit, does not exist. So the two-sided limit, which doesn't have any sign in the power position, does not exist. It does not exist because the two one-sided limits do not agree. Are there any questions about that? The two one-sided limits do not agree. Okay. Now let's take a look at the limit as x approaches -8. So locate -8 on your graph, which is here, and I'm going to have to scroll it up a little bit so we can see the whole thing. We can see that at -8, we have a displaced point. The point is defined at -8, but it's up here at -3, and that's not where it looks like it's going to hit. Go to both sides of -8 because it's a two-sided limit. Trace your fingers as they get closer and closer to -8. What does it look like it's going to hit? Well, it looks like it's going to hit the y value of -6. So that's the limit. Even though that's not where it actually hits, that is the limiting value. So this is going to be -6. Be very sure you understand that the limit is what it looks like it's going to be, not what it actually is. So in a sense, the limit is like a pattern. And we're continuing the pattern. This is where it would be if it followed the pattern. Okay, the next one I want to look at is the limit as x approaches 0. So 0 on the number line is in the middle. Trace along the curve from both directions. It looks like it hits about, what would you call that? 1.25, maybe? Something like that. All right. Now we've got a series of ones that are looking at the limit as x approaches -2. So we've got 2 of those. The limit as x approaches -2. So find -2 on the x-axis. And I had one of them over here. The limit as x approached -2 from the right, we said was positive infinity. What's the limit as it approaches from the left? So I trace along the curve from below -2, and it looks like it hits 3, and it actually does hit 3. So the value is 3 from the left. But I've got 2 one-sided limits. I've got the limit from the right, which is infinity, and the limit from the left, which is 3. Those don't agree. So the 2-sided limit at -2 does not exist. Right? I think the last 3 are all one-offs. We have the limit as x approaches 2. There's no sign in the power position, so it's a 2-sided limit. Locate 2 on the x-axis, find the graph, trace along the graph from both sides of 2. It looks like it hits 3. So I'm going to guess it's about 3. And then the limit as x approaches 7. So I'm going to locate 7, which is halfway in between the 6 and the 8, which is right up here. It looks like it's at the top of this maximum here. And that looks like it's about 5.5. And the last one is the limit as x approaches 10. So from both sides of 10, that means from the left, we're tracing down this upward part. And from the right, we're coming up this part that's below the axis. And they both converge on the same location, which is at 0. Now, this is exactly the kind of thing that I would ask on a quiz or an exam. I would have a problem just like this one and ask you for all kinds of different values. So this is a very, very, Caleb's like, oh no, I wasn't paying that much attention. Yeah, no, this is exactly why I spent so much time on it. This is exactly the kind of thing you need to be able to do, to read it off a graph. It's very important. All right. And I do have another couple of opportunities. We want to draw the graph of f of x equal 1 over x squared. And then we're going to find the values as x approaches 0. The 2 one-sided limits from the left, from the right, and then the 2-sided limit. So let's graph that first. So I'm going to get rid of some of what I have on here because it's getting kind of full. So I have the graph of y equal 1 over x squared. All right, which looks like this. So we can either hand draw it or we can take a picture of it and paste it, whichever way you'd like to go. You can do that for your picture. I'm going to copy and paste since I am better at that than I am at hand drawing. Drawing is not my forte. All right. So now we're looking at the picture, and the question is, what is the limit as x approaches 0 from the left? So locate 0 on the x-axis, find the picture to the left side, and trace along it. It looks like it's going to positive infinity. So my limit up here is positive infinity. Then we have the limit as x approaches 0 from the right. So I approach from the right, and this looks like it's also going towards positive infinity. So I write positive infinity. And then the 2-sided limit does not have a sign in the power position. The 2-sided limit only exists if the 1-sided limits exist and agree. They don't exist, but they do agree to go to infinity, but remember that technically means it does not exist because infinity is not a number. The limit is supposed to be one finite real number. Okay, one finite real number, and it's definitely not. Okay, let's repeat the process and let's look at the graph of 1 over x cubed. So we're just going to change the power from x squared to x cubed, but that has a big effect on the graph. It basically makes it look like a rational function. So like 1 over x, except it goes faster than 1 over x does. So it looks something like this. Right, so we have the graph right here. So now we're talking about the limit as x approaches 0 from the left. So here's 0. We want to approach from the left side. And we can tell from the left, because it's cubed, it's going to maintain the sign. And so we have a negative, a negative, negative. And so this is going towards negative infinity. And what about the limit as we approach 0 from the right side? Approaching from the right side of 0 on the number line, trace along the curve, and it's going up forever because the values are all positive. And when you cube a fraction, it gets larger and larger. And so this goes to positive infinity. Now, the two-sided limit can only exist if the two one-sided limits exist and agree. These don't technically exist and they don't agree. So what's the only solution you could write down for the two-sided limit? What do you have to write for that?
Does not exist.
Yeah, thanks, Michael. So D and E does not exist. All right. Now there is a pattern to the ones that we've been looking at, which is 1 over x minus a to the n, where n is a positive integer. So if we're talking about taking some rational expression where you've got x minus a number raised to some power in the denominator and the power is positive, because otherwise if it were negative, it would actually be in the numerator, right? It would change. It has an effect on the limits as you approach from the left or the right, depending on whether n is even or odd. If n is even, then it's like squaring it or raising it to the 4th power or the 6th power. It will always be positive. And in that case, it's going to look like this graph on the far right. All right. So this is for n being even. On the other hand, if it's odd, then on the right side of a, it's going to go up to infinity because x minus a will be a positive value. And on the left side of a, x minus a would be negative. And so that would make it go down towards negative infinity because it's raised to an odd power. So it just depends on what you've got. Okay. All right. So let's take a look now at drawing a graph from limit information, which is going to be slightly different. We want to draw a graph that fits the information that's given. So this is a little bit harder to do. And there's no one right answer. There are infinitely many graphs that you could draw that would fit the information. But what we're going to do is draw the minimum. So this one says it looks like the limit as x approaches 2 of f of x is 1. So that means one of a couple things. It could mean that it is 1, right? That when x is 2, y is 1. Or it could mean there's a hole there, or it could mean there's a displaced point there. But at any rate, it looks like as x approaches 2, the y value is 1. So as x approaches 2, it looks like the y value is 1. So either it's a hole, a displaced point, or it actually is the point, all right? So you have a choice. You can make it a hole, you can make it a displaced point, or you can fill it in and make it solid. So I'm going to fill it in and make it solid, right? That comes from the first piece of information. The second piece of information says the limit as x approaches 4 from the left looks like it hits 3. The limit as x approaches 4 from the right looks like it hits 6. That looks like a jump, right? Because I've got two different values. I've got one value from the left and one value from the right. So that's going to be a jump in the graph. And then it says f of 4 is not defined. So I don't have a solid ball at 4. So from the left, it looks like it hits 3. So from below 4, I want to come up and look like I'm going to hit 3, but I don't hit 3 because it's not defined there. And from the right, it looks like it hits 6. So I'm going to come over and I'm going to draw a ball from the right at 6. And then I'm just going to complete the rest of it with something to make it look like a function. That fits the information. Is that the only thing I could have drawn? No. I mean, I could have drawn a lot of things. I could have, if I'd wanted, taken this part and gone down with it, or I could have taken this part and I could have gone up, or I could have just left it off, right? And the same thing on the right, okay? Okay, let's fit this piece of information onto the graph. So we've got a lot more information here. As x goes to negative infinity, f of x goes to 2. X is going to negative infinity. That would be off to the far left. And the function value is approaching 2. So we're going to put an asymptote. So it's got to get close to that on the left. And then it says the function value as I approach 3 from the left is negative infinity. But as I approach 3 from the right, it's positive infinity. So I've got to have a split of a vertical asymptote where one's coming up and one's coming down at 3. So I've got something here. And one of them is going down from the left side. And this one's going up from the right side. All right. And then it says as x goes to positive infinity, f of x approaches 2 again. So that would be off to the far right of the picture. It's going to get close to 2 again. And the last piece of information is that f of 0 is negative 1/3. Well, let's see, this is 1, so that's half. So that would be about here. So I'm going to come up and I'm going to hit here. And then I'm going to get close to that like that. And then this is going to just come down and approach that line. That works. I mean, is that the only graph? No, that's not the only graph that you could draw. There are lots of graphs you could draw, infinitely many, but that does fit the information that was given, right? We have two important limits that we want to take a look at. And for some reason, I didn't put a whole lot of examples into the notes, but we do want to take some time and kind of look at these for a little bit because they're going to show up in the homework and they can be quite challenging. So I may handwrite some additional limits in. So limits that exist, the trig limits, and actually they may not be in this section, we'll see. We're going to be looking at a better way to find them, but there are two equations that are pretty unique that we have names for. This is called the identity function. And you should definitely memorize any function that has a name, all right? And this is called the identity function. It's the line y equal x. And it's important because everything that has an inverse has the inverse on the opposite side of this line. It's the only function that is its own inverse 3 ways. Equation-wise, if you swap x and y, you still get x equal y. If you swap the ordered pairs, if you swap 1, 1, you still get 1, 1. And on the graph, if you form the mirror image of it, is itself. It's the only graph that does this. All right. So it has a name. It's unique. It's called the identity function. Because it is the identity function, what you put in is what you get out. So if I put in a 4, I get out 4. If I put in 10, I get out 10. So the limit of the identity function as x gets close to a is a, all right? So as x approaches a, the value is a, because on the graph, no matter where I am, if the x coordinate is a, then the y coordinate is a. It's the identity function. The other one is the constant function, which is not unique because there are infinitely many of them. It's just a horizontal line. All right, so any horizontal line is called a constant function, and this is y equals c. That means that no matter where you are on that particular graph, no matter what the x value is, the y value is always going to be c. All right, so you have x1c and x2c. No matter what value x is getting close to, the y value stays the same. It is constant. So you should know that that also always comes out to be c. All right. So those two are pretty important. Can you tell from the graph why that has to be true? I mean, they're pretty straightforward, but just to be sure. All right. And now we want to talk just a little bit about limits that do not exist. So we'll talk about these for just a second. Here is a graph of a sine of 1 over x. And I know that some of you are struggling with finding domain and range. This is actually a pretty important skill, but it's one that we practice kind of hit or miss. So I don't think students ever quite get it down. When you're looking for domain, you're looking for all the values that x can be, which basically means what can x not be? So you're looking for two things usually: 0 in the denominator, negative under a radical. Those two things. I don't have a radical, but I do have a fraction. So what value can x not be here? Can't be 0. If x is 0, I'm dividing by 0, and thou shalt not divide by 0. So the domain is going to be all values except 0. To leave 0 out of the domain, draw a curved parentheses, like half of a whole, then put a union symbol, then open it up and mention it again, going off to positive infinity. I like to think that what you're really doing is drawing a hole around that number, the 0, and you crack it open and you turn them inside out, and that forms the two halves of the open parentheses symbols. Do not use a square bracket. A square bracket includes the number, and we want to exclude the number. All right?
Oh, I
So
have a question.
Yeah, Juan.
Can we write like the R of all real numbers and then 2 points and then minus, not 0?
You can also do that. Yes. Yes. In web work, though, occasionally they're going to ask for interval notation, and that's how you write it. The fastest way, though, obviously, is to do a double bar R, which represents all reals, and then not equal to 0. Okay. Why do you think there's a limit here as this function approaches 0? Is there a limit as x goes to 0 of the sine of 1 over x? What do you think that turns out to be? Or do you think it doesn't exist? Look at the graph and imagine what sine does. It's oscillating.
It's hard to tell because
It's hard to tell, but
every, like, I don't know how to say it, but yeah, it's hard to tell.
It's still going between -1 and 1 and oscillating faster and faster, so it does not exist. It never settles down to one finite real value, so it does not exist. due to oscillation. All right.